So the next talk in the Worms of the World virtual event will be on the giant wetland worms of South America. And I'm delighted to welcome Rumsaïs Blatrix from the Center for Evolutionary and Functional Ecology at the University of Montpellier. And Rum is an ecologist that's mostly interested in species interactions and specifically two kinds. So the mechanisms of interaction between individuals and their evolutionary significance, with a focus on disruptive pollination and ant plant symbiosis, and also the consequences of interactions at the landscape scale. And that's with a focus on the role of soil organisms in patterned landscapes, which seems to fit quite well with this title slide. So I'm going to hand over now to you, Rum, and I look forward to hearing your talk.
Okay, thank you, Karen. So the talk will show some work we have done together with Doyle McKee and Delphine Renard. We are forming an informal team, and we are interested in figuring out how spectacular landscapes can arise from the activity of soil organisms, and in this case, I will talk about earthworms. So these spectacular landscape I was mentioning are earth mound landscapes. So basically, here are a few examples of earth mound landscapes that you can find in South America, but they are also common in other parts of the world, such as Africa, and well, a little bit everywhere actually. And you can see that they consist in numerous mounds, regularly spaced, and they have several kinds of origins. And for some of them, the origin is not even well known and is a question of debate. Among the examples that we are studying, you have the raised fields. I guess you can see my cursor here. So these are archaeological vestiges of raised field built by pre-Columbian civilization, and they consist in small mounds. They are about 1 or 2 meters in diameter and 50 centimeters high. And they were built for growing crops, mostly for concentrating nutrients and also for escaping floods. We have studied them in French Guiana and also in the Llanos, Moros, and Bolivia. Another type of earth mound landscape are the morundus in Brazil. We have not studied them, but they probably result from the activity of termites, but the origin of the morundus is still debated. The most widespread earth mound landscape that you can find in America and in Africa are the termite savanna, in this case, each mound is a big termite nest, and they can be up to 30 meters in diameter and 2 meters high. So they are conspicuous on satellite images, which is not the case of most of the raised fields, the pre-Columbian raised fields that are too small for most satellites. Another interesting case of earth mound landscapes are the sartenerales. The sartenerales are much smaller. They are about 20 to 50 centimeters in diameter and 10 centimeters high. And we believe, well, they are not very well studied, and we believe that they arise from the interaction of soil organisms and plants. And the last one I will talk about are the surales, and this will be the topic of the talk. So the surales are mounds that are about 2 meters in diameter and 50 centimeters high. They are quite similar to the pre-Columbian raised field, but they are built by earthworms. At least that's what we think. So yeah, one common point to all these landscape is that they occur in very flat lands that are seasonally inundated. So the flooding seems to be an important factor in the genesis of earth-mound landscapes. So the Surales landscapes, they occur mostly, well, actually they occur only in the Llanos del Orinoco, in Colombia and in Venezuela. And the work we have conducted up to now was in Colombia. So if you look from the sky, you can see what the landscape looks like. It's a lot of earth mounds, and it's very impressive because it covers very huge areas. For example, here, each mound is about 2 meters in diameter and 50 centimeters tall, but there is variations. I will show you some other pictures later, and you will see that it's very variable. And from the ground, it's looked like this, the small image on the top right. And so the top of the mounds are not in the water during the flooding, but the rest of the basin is under water. So the Surales landscapes, most of the time you can't see them from satellite images. For instance, on the right, you have here a picture of the being satellites, and it's very difficult. But if you are a little bit trained, you can figure out that here are Surales. In other places, it's easier to see them, but it's not the main case. So that's probably one of the reasons why very few people studied the Surales landscapes, because they can barely be seen from the data available. And so we try to figure out how much surface area they cover, and using satellite images. And even if most of the Surales cannot be detected from satellite images, still we recognize that in the Llanos del Orinoco, there are about 75,000 square kilometers that contain Surales landscapes. It's about 2/3 of the Llanos del Orinoco. Most of them are in Colombia, and they are also present in Venezuela. So it's a huge area. And so a fairly common landscape in this Llanos. So here comes the worm. The mounds are built by a giant earthworm, an Andiorinus species. It's an undescribed species, and actually, when you dig in the mounds, you find only this species of earthworm. And according to the local people who are interested in earthworm, of course, they say that these species of Andiorinus can only be found in the Surales. And so in the we don't know anything about this earthworm actually, but it's interesting to see that in Africa there are similar landscapes that maybe can give some idea of how it works. So let's go to Africa and see what we know about earth-mound landscape built by earthworms. So in Uganda, there are swamp areas that are known to be covered by earth mounds that looks very similar to the Surales. So here is a picture from 1959. It's actually the only picture I found showing the mounds. So it's a bit difficult to to figure out what they look like, but according to the description in this publication, they sounds to be very similar to Surales. And from the satellite images, we have, of course, nothing very conspicuous, but we are used to it. And for me, this picture displays a landscape that is typically similar to Surales. And so there are very few publications on this landscape in Uganda, but still some people were interested in converting this land into flatlands for rice cultivation. And so they studied the earthworm because they wanted to know if the land would be suitable for rice cultivation, even if they would destroy the mounds. And so we have some information. So these mounds are built by swamp worms. In particular, the species Alma emini. So at that time, it was considered a member of the Glossoscolecidae, but I just learned from Sam James' talks that they have their own family now, the Halmidae. And they are peculiar because they have a system, they live in the mud, in waterlogged mud, and so they need to get oxygen and to respire, to breathe. And so when they need to breathe, they put their tail above the level of the waterlogged mud, and they flatten the tail and expose what we call a lung. It's a very vascularized tissue. And so flattening allows to increase the surface, the interface between hair and the cuticle of the worm. And so they can also fold the side and build like a small funnel that they can retreat in the burrow, and so they can brace without being exposed to predators. We haven't seen this in the Andiorinus from the Surales, but it's interesting because the people who studied this earthworm in Uganda, they dug into the mounds, the earth mounds, and they realized that the worms were really living on the mounds and below the mounds, but never in the side, in the matrix, in the basin. And so they conclude that the mounds have been built by the worms. And so that's probably the same mechanism that occurs in Colombia. So let's go back to Colombia and try to understand how the Surales forms, how the mounds are growing. In some literature, we found that people consider that the Surales are the result of an erosional process. Sorry. So for them, for Gusen in particular, in 1971, erosion was the main mechanism shaping the mounds of the Surales. But our hypothesis is different, and we have done some field work to figure out, to get arguments for hypothesis. We consider that there will no or little export of soil out of the system due to erosion, but rather that there is local redistribution of the soil, and this due to the activity of the worms. And so where we show you some pictures and some sketch of the process we believe is at the origin of those mounds. So first, the worms feed on organic matter in the flooded soil, and as they need to breathe, they build small towers that are made of casts. And so that allows them to reach the surface when the water is not too deep, when there is shallow water. But as they are anisic worms, they have a permanent burrow. And so as with time, the tower is growing because they accumulate casts at the surface always at the same place due to their permanent burrows. And so as the tower grows, it makes, they can coalesce with the neighboring towers, and that would form low platforms. So here is a picture, an aerial pictures, and of a very interesting part of the savanna. On the left bottom corner, you can see the individual towers that are not yet coalesced. But when you move to the top, to the right, you will see that the different towers have coalesced to form a bigger platform, bigger mounds. And if you look from the ground, it looks like this. And as the towers coalesce, they get covered by herbaceous plants, by grasses. So in these pictures, you can even guess where the individual towers that coalesced to form a mound. Here we can find 1, 2, 3, 4, 5, 6, 7 of them. So later in time, the mounds, the platform will grow in height because of the activity of the worms that bring more and more material to the surface. And as the mounds are growing in height, the intervening matrix, the basin here, is going deeper because actually it's a working hypothesis. We have no proof of this, but we believe that the material, the soil that is brought to the surface comes from below the mounds and probably below the basin, the matrix here. So there is a transport of soil from the basin to the mounds. In some places, the mounds are really big. They can be up to 4 or 5 meters in diameter and 2 meters high. And at this point, they are covered not by grass, but by trees. As they grow, they can sustain larger trees. And if you look on the side, you can see that they are made of earthworm casts. So we build a verbal model for the formation, and I will just summarize this with a sketch. So at the origin, you have a flat soil. Here the yellow line, and which is seasonally inundated. So there is shallow water. So if the water is too deep, the earthworms cannot build the tower to breast, and actually they cannot live in places where the flow is too high or too long. And as the result of the worm activities will build a tower that will go above the surface of the water, and so that will allow the swarm to breast. And to build this tower, the surrounding of the tower will go deeper. And as the tower grows into a mound, the area right around the mound is getting deeper and deeper. And so in this area, no other tower could grow because it would be too deep for a worm to initiate a new tower. And so that would explain why we see mounds that are regularly spaced. So yeah, this is a variable model, and we want to formalize it mathematically. So we have obtained a National Geographic grant to study the biology of the life history traits of the earthworm, to try to put numbers on all these parameters that we have here. So which amount of soil does the worm move, and so on. And so that will be the next step. And yeah, that's actually we don't know much about the functioning of these landscapes and the role of the worms, and so we have many open questions. And for instance, one of the questions is what limits the final age of mounds? What happened after they reach a size of 4 or 5 meters in diameter and 2 meters high? Maybe we have an idea with what happened here. As you can see that there is erosion below the roots of the vegetation. Maybe they finally collapse on themselves. Another open question is what determines the regular size of the coalescence? And so our hypothesis is maybe that this particular earthworm has a gregarious behavior that would explain why all the mounds are the same size. Maybe they can aggregate to a certain number that will explain this peculiar pattern. But as we know nothing about the species of Orinoco, right now we cannot answer. But this is something that we want to investigate in the future. Another question that maybe is the most interesting for an ecologist is what explains the variation of the Surales shapes. Here, for instance, it's an aerial picture, and you can see that at the bottom left corner, you see individual mounds, but when you move to the top right corner, you see a very different patterns. And this is correlated with the topographic gradient. In this place, the soil is the landscape is really flat, but there are very small topographic gradients. So maybe there is 1 meter difference between the two corners of the pictures, but it's enough to induce drastic changes in the shape of the Surales. So to investigate this issue, we will rely on the activator-inhibitor principle that was proposed by Alan Turing in the 50s to explain the patterns that you can see, the regular patterns that you can see on animal coats like the guépard, the cheetah, or in vegetation spots in ecosystems. So this principle is based on the fact that regular patterns can arise from the interaction between positive feedback at short scales and negative feedbacks at longer scales. And so this seems to be a good starting point to investigate the shape variation of the Surales. Because if you look at modeling of this principle, mathematical modeling, you can see that the expected shapes of the regular pattern depends on the strength, on the scale of the feedbacks, and it really strikingly matches what we observe from the sky in the Surales. And so this is one of the thing we want to investigate. And yeah, so maybe I will to do this, we need to take IO picture, and actually we have been doing this for a while, and I will show you a picture of your previous system for taking IO videos.